All right, now we're on lesson 8 through 12 of Unit 3, and this lesson is all talking about similarity of shapes, and how we can prove something is similar, and then what we can do with something once we know they are similar. So previously in last lesson, I showed you what the symbol for congruence was, but there's also a symbol for similarity. So let's go ahead and get that down in our notes. So we saw last unit that the symbol for congruence is an equal sign with a little squiggly on top. Similarity is very similar, it's just that little squiggly, because they aren't exactly equal. So it's taking the congruent symbol and taking away the equal sign, because the shapes that are similar are not actually congruent, they're not equal, but they have very similar traits, mainly the angles. And that's why we have this symbol minus essentially the equal sign, okay? So now let's look at these shapes that I have below. So here we have 3 triangles, and I have the directions essentially said 3 different ways because I want to show you all the different ways you might see this being said, but it all means the same thing. So describe a sequence that maps A onto C, or you might hear it as describe a sequence that shows that A is similar to C, or you might hear it said as describe a similarity between A and C. All this means is show how we can get from A to C. So let's write that down. So just show us how we can move A to become C. And this is very similar to Unit 2, which is now we're also including dilation. And that's why instead of describing a congruence, we're just describing a similarity. So we're still doing reflections, rotations, and all of that. We're just also throwing in dilations. And that's why you can end up with shapes that are bigger or smaller than your original. Okay? And just like in last unit, sequences have so many varieties of answers. There are so many ways that you can get from one shape to another. For this one, there really is only one way because I'm showing the in-between shape to help us see what order they might go in. But later on, you'll see that if we're just given the first one and the last one, there's so many things that you can do in between to get from A to C. So first, let's start with how can we get from A to B? Well, just looking at this, most of us recognize that we need to reflect it, right? Because your orientation becomes the other way. So we need to figure out where our reflection line is. And if you have a mirror, that's really, really easy to find where that reflection line is. So let's go ahead and use our mirror, or you can just kind of sketch it because I know you're at home doing this without a mirror. All right, so using our mirror, or maybe you just kind of guesstimated where it's going to be, we found that there is our line of reflection right down the middle. Okay, so let's write that in because we need to be very specific when we do these sequences so we know what we're talking about. Okay, now this is good enough saying that our first step is to reflect across this line. Okay, a lot of you got 2s and 3s on your last test because all you would say is, oh, reflect, or maybe you would just draw the line and you wouldn't be a little bit more specific. Okay, now that we're at B, so we know how we got from A to B, now we need to figure out how we get from B down to C. Okay, there's definitely a dilation going on because it's getting smaller, and we know how to find a center of dilation based on the last lesson. We just need to connect the dots and see where they cross. So let's go ahead and do that. Okay, that was actually pretty hard because I didn't give myself enough room, but they actually cross right at the bottom of my board, and you can barely see it at the bottom of your screen. But hopefully if you're following along at home, you're going to get the same thing. And you'll notice I didn't actually have to do every single point. All I had to do was 2 because they're all going to converge on the same point. But you can do all 3 if you want to. This is going to give you the same answer. So now we can say that we need to dilate as our second step. Okay. Now in high school they'll want you to find out what the actual dilation is, what the scale factor is, if we're dilating it down by a half or a third, and we can easily find that by measuring things out. But for our purposes, I just want you to know that there is a sequence to get from A to B. So this is enough to say that first we reflect it to get from A to B, and then we dilate B down to the center of here to get C. Okay, and that's good enough. And if you want to find your scale factor, you of course know how to and are welcome to. All right, let's move on to these sentences down below and finish these up. All right, here we have it says if A is similar to B, then B is similar to what? And this is actually a pretty obvious statement. So if the shape of A was similar to B, then B is also similar, of course, back to A. So you can go both ways. Obviously, if A is similar to B, then B is going to be similar to A. The second statement here says if A is similar to B and B is similar to C, then A is also going to be similar to C because they're all similar to each other. Okay, that's the whole point. So the first one can be similar to the second one, B, and then if B is similar to the third one, C, then A is also going to be similar to that last one. And we actually saw that by just doing those isometries. Those transformations. So now we have this last statement. Shapes are similar to one another if gotten through a transformation. Last unit, we talked about how things were congruent if they were gotten through an isometry. Okay? But dilation is not an isometry because it doesn't keep the shapes the same because we're shrinking them or making them bigger. So things can be similar if they're gotten through a transformation. So that's all of our isometries plus dilation included. We can say that those are similar as long as we got through a rotation, a translation, a reflection, or a dilation. We can say that they're similar if you get it through those four things, those transformations. All right, now let's take a look at if we're missing a side length of similar triangles. So we're told, we just know that these triangles are similar to each other. And we're told that the scale factor is 2, okay? We probably could have figured that out looking at 12 and 6. Okay, so we need to figure out what x and y is, knowing that our scale factor is 2 and that these are similar triangles. Well, that's actually pretty easy because if we notice going from 12 to 6 that it's essentially half, then we need from 13 going to y, we just need to divide 13 in half. And we can leave it as 13 over 2, or we can actually make it 6.5. So y is 13 over 2, or 6.5. And same thing down here, 5 going to x, we just need to take half of 5. So x is going to be either 5 over 2, or we can put it as 2.5. Okay? So if we know that the triangles are similar, and we have our scale factor, or at least we can recognize what the scale factor is just looking at the numbers, then we can figure out those missing sides. All right, here we have something called the Aaa Criterion for similarity. Okay, so I'm going to get to what that is in a second, but let's start with some basic information. Triangles are similar to one another if the angles are the same. So if all the angles of a triangle are the same, then we can say those two triangles are similar. So this is a good example of it. Both of them have a 70, both of them have a 60, and both of them have a 50. So those two triangles are going to be similar. They're definitely not congruent. They're not the same size, but we remember that angles are preserved through dilation. Okay? So the angles are going to stay the same if we dilate them, and that keeps them similar. So even if they're not quite looking exactly the same, as long as they have all the same angles, they're going to be similar. So here we have a 41, here we have our 85, and here we have our 54. So these two are still similar, even though the orientation of them look a little bit different, they still are similar. Okay? So now let's look at the actual Aaa criterion for similarity. So what that means is we don't actually need to have all three angles. Think about it. If I took away one of the angles of a triangle, we still really know what that is because we learned last unit that if I have two of the angles of a triangle, you can automatically figure out what this last angle is. So what the Aaa criterion means, which stands for angle, is essentially saying you only need two angles to prove that triangles are similar. So as long as it has two, it says that if you have two angles that are the same, then the triangles are similar. So let's get down that definition. All right, so I put this down just so you remember that the Aa stands for angle, meaning two angles. So triangles are similar if they have two angles that are the same. That's all that means, okay? We just need two angles in order to prove that two triangles are similar. So now let's take a look at some of the examples below and see if we can use this to prove if they are similar to one another or not. All right. Let's take a look at our two first sets of triangles and see what we can see knowing about the area criterion for similarity. So our blue set of angles, we have a 72 for each of them, and then we have a 35 also, as well as for an angle. So that goes right into our definition of Aa criterion for similarity. We have two angles that are the same for each of them, so these two triangles are similar. That's textbook Aa criterion. Now let's take a look at these ones over here that I've color-coded red. So we have two 70s, awesome, we're halfway, but then we have an 80 and a 30. And I know most of you are going to want to jump and say, okay, well then they're not similar. But let's take a look at what the missing angle is, just in case. So we know from last unit that the interior angles of a triangle adds up to be 180. So if we have 70 here, 80 here, what's missing to make up that 180 is 30. So this angle needs to be 30. So let's take a look at the missing angle over here. Again, the interior angles need to add up to 180. We have a 30, we have a 70, which adds up to 100, so missing from 180 would be 80. So now let's take a look at our angles. So we have two 70s, we have two 80s, so already we're actually saying that yes, they have to be similar, and we also have two 30s. So not only are these triangles similar through the Aa criterion, they're similar because we have all the angles, so of course they're similar. So don't get thrown off just because they give you two other angles, because your book will try to mess you up like that. All right, let's take a look at our last example. All right, with our last example, I know that the angles are a little fuzzy, so take a second to write these in if you need to. This top one is 31. This side one is 103. Down here, this is 85. And up here is 31. So now let's take a look if we can prove that these two are similar or not. So we do have, first off, 31s are the same. So now we just need to make sure that there's another angle that is also the same, then we can say they're similar. Well, the 103 and the 85 are not the same, but hopefully the missing angles will help clue us in. So again, interior angles of a triangle add up to 180. So we have 103 plus our 31. So we're up to 134. We need to take that away from 80 to figure out what we're missing. So we're missing an angle of 46. So that's what that angle is. So let's see then if we can match that up over here. And some of you are already saying it's not going to match up because neither of those angles is 85. But let's follow through anyways. So here we have our 85 and 31. Add those up. And we get 116. So now we take that away from 180 to find out what's missing. And we're missing a 64. So this angle is a 64 degrees. So now we can definitely see that these are not similar. Just because you have one similar angle does not mean anything. You need at least two. And none of these remaining ones are similar. So these are not similar. And a lot of you saw that right away. They don't even really look like the same shape, but you have to remember sometimes in our book, they'll just kind of throw numbers in and they won't be to scale, so you can't always judge based on how it looks. You need to do the math yourself. And that is actually it for this lesson.